Thank you for coming today. In this third lecture, I will give you some precise results when we assume that inside our wells we have what we call meta points. Okay? Good. So our problem is we have a state space, a sequence of state space, finite state space, over which we have fixed a partition. Phi is just the projection function. And we have fixed a sequence of Markov processes. And I will assume that all these Markov processes are irreducible. Okay? And we are interested in this process, which is the projection, just a projection, according to this partition of the state space of these Markov processes. Okay? So let me call mu n the unique invariant measure for this Markov process. Let mu n be the stationary distribution of the Markov process. Good. So once you fixed a point here, and you see x and t as a function on the time, on t, then what you see is a path, a trajectory over this state space S. So we can think of xn as a random variable taking values on the path space, the set of Cadillac functions defined over this set S. And our question is find sufficient conditions to assure that this sequence of random points inside this set converges to some other random point inside this path space. Okay, so if you want to understand the convergence of random points inside this set, first, obviously, you need to understand what convergence of deterministic points is here. Okay, so let me fix the topology in this space. First, I need to fix a topology here on this state space S. This is finite, so for S we assume just the discrete topology. Actually, I will use just the absolute value distance here. And for the path space, I will use the Skorohod topology. Good. So in this sense, in the Skorohod topology, is that I will prove that this sequence is convergence to these stochastic processes in the sense of distribution, in DOE. Okay? Okay, so this is my question. And now I will prove that, proving at first that this sequence is tight. I mean that for any subsequence here, there exists a further subsequence converging to somewhere. Okay, this is what I will first prove. And then secondly, if you have two subsequences such that they are converging in distribution to some random paths, then they have the same law. So in my second step, I will prove that actually the law of the limit must be unique. Okay, after these two, if you have these two results, we can conclude that actually xn is converging to this unique law. Okay, for one, here we need to prove that the sequence is tight. So I will use something that is very standard, Aldous criterion. Aldous criterion. Okay. The sequence xn. Okay. So let me remark that you are looking at this sequence of random variables. So you are looking at a sequence of trajectories, at paths. Okay. And you consider the topology, the Skirhov topology for this set of paths. Okay. Now Okay, the sequence will not be tight if you observe for xn, for the path of xn, something like that. So if you observe that, for example, you process some time it jumps, and then very, very, very quickly it jumps again. So let me call tau n this time in which the process is jumping, and then the second jump occurs very, very, very fast. So if you observe that for your sequence of xn, then for sure the sequence will not be tight. So the Aldous condition is the following thing. Let me write here x tau n plus t minus xn tau n. So this is the size of the jump. The size of the jump after this time t. Yep. Of the size of the second jump. Oh, I mean, not second jump, but almost that. How you move after the first jump at time t. Okay? How far you move. Okay, so in the Aldous condition, the Aldous condition is to assure that when you take a sequence Tn, let me call this Aldous condition. When you take this sequence of times Tn, a sequence converging to 0, you are able to prove that for any stopping times, for any sequence of stopping times, bounded stopping times, so you fix an arbitrary you fix an arbitrary time t, deterministic t. So in the Skorohod topology, it's enough to analyze, to examine your path just on this time, interval time, compact interval time. So for any Tn going to 0, for any sequence of bounded stopping times, if you are able to prove that the size of this displacement is going to 0 in the sense of probability, then you will get the tightness of the sequence xn. So this is the Aldous condition, and I claim that the Aldous condition plus the fact that S, the state space of this sequence of stochastic processes, is compact, these two facts ensure that the sequence is tight. Okay, so this is the theorem of Aldous. And here S is trivially compact, and so this is what I need to actually prove. Okay? Good. But now, remember that. So this is the Aldous criterion you can apply for any sequence of stochastic processes. Okay? But here, these stochastic processes xn are functions of this Markov process. So I will use that I have a Markov process here, and I can write this difference by using the Dynkin's martingale for this for the Markov processes eta. So this difference is you can write this difference as you have an integral here, the integral from this time to this other random time. Okay, these are stopping times, these are deterministic times. Eh? Okay, they are very similar, but okay. Of what? Here we apply the generator of this Markov process to the function phi. So yesterday we made this computation. Recall that, so we will obtain this xn s. Here the rate of this transition is q of eta n s to e j. Yeah? And now you need to sum over all the possible j. Yep, it's good. ds plus the difference of a martingale difference. That's a martingale difference. Okay, so if you want to prove that this difference is going to 0 in probability, it's enough to prove that this other difference is going to 0 and that this integral is going to 0. Okay? Let me tell you that actually I can give a precise expression. This is tau, this is t. Sorry. I can write a precise expression for the expectation of the square of this difference. This is equal to the expectation of the integral from tau n to tau n. The integral over this time integral of now you have the square of these transitions times the rate. Good. Okay, this is something also very well known. I'm sorry, I will not prove that. These are just the quadratic variation of the martingales, the Dinkin's martingales associated to a Markov process. This is something somehow standard, so you can find this equality in some book talking about the Dinkin's martingales. And now, in order to prove that this is convergent to 0, I will try to prove that that martingale difference is convergent to 0 in L2. Let me write. This expression is very similar to this other expression. Here, I will take the L1 norm of this unknown variable. And so I will try to prove that this L1 norm is convergent to 0. Okay? So in order to prove that this is convergent to 0 and this is convergent to 0, you can believe that it's enough to prove so. It's enough to prove that. Okay. These numbers are uniformly bounded. You have just a finite sum here. These are also uniformly bounded. So it will be enough to check it will be enough to check that the integral of these functions is going to 0. Okay? I will forget these terms because they are uniformly bounded. Now you have here an integral from stopping time. Okay? At this point, you can use the special case in which you have this here Markov process. So you can use the Markov property to shift all these processes to the time 0. Okay? So believe me that it will be enough to prove that the expectation of an integral from 0 to Tn of just this term okay, this is positive, so I don't need the absolute value, is going to 0. But of course, when you used the Markov property, you don't know the starting point, the new starting point, I mean the position of the Markov process at time tau n. So we need here to take, or to prove this estimate uniformly on the starting point. So let me put here an x just to remember that your Markov process eta is starting at this point x. Okay, this is what we actually need. Can I erase that? Okay, let me finish it later. Suppose that we have proved that. And now let's move to the next step. Okay. Okay, so suppose that you already have proved your tightness and fix some subsequence of x. fix some subsequence converging to some limit, and we will try to characterize this limit. Yep. To prove that the law of this limit must be unique. So suppose that, to keep notation simple, suppose that let me call this subsequence, this arbitrary subsequence, xn chance xn, in order to avoid a k here, which is annoying. So suppose that the sequence xn is converging to something. And now I will prove that the law of this x, it's only, you only have one possible law for this x. Actually, this x will be, the law of this x will be the law of a Markov process with some transition rates. Okay, so you have this convergence in distribution. But you know that by the scatter representation theorem, this is not really necessary, but I like to use this theorem. So scatter representation theorem. You can suppose that actually this convergence is pointwise. Okay, and here is the convergence in the scatter topology. Okay, very well. So fix some test function on the space in which x is moving. And now we know that for xn we have this linking martingale. Yeah, we have our linking martingale. That means that this is time. Let t1 be some time, t1 some time later. Look at so this is the linking martingale for the Markov process, and corresponding to this function f. Actually, f of the composition of f and the projection function. Look at the difference of these two martingales at these two times. You know that the difference of these two martingales, the expectation, the conditional expectation of this difference, condition on this sigma field before T1 is equal to 0. This is just the martingale definition. And so I can say that the expectation of this difference, so let me write the difference, is f of eta t1 minus f of the process at time 2, sorry, t1 minus t2, t2 minus t1, minus, okay, the integral here. I need more space, but I will try to write here. Expectation, so f of eta t2 minus f of sorry, f of x and t2 t1 minus here the integral from t1 to t2 of f of j. Here I will sum over j. Minus f of n s. And here you multiply this difference by q n eta. Yep. Ts. So this is just the difference between these two martingales, okay? If you multiply that times a function of the position of the process X at some times which are here before the time t1, just by the definition of martingale, this expectation must be equal to 0. Can I move this? Sorry. Okay, everybody can see this expression. It's okay? Okay, good. So this is what you have for xn, and we would like to obtain a similar thing for this limit x, in order to say that x is also a solution of the martingale of some martingale problem. If I take here the limit when n as n goes to infinity, then these terms will converge just to f of x. Okay? Also here, this will be converging to the same function g applied to this vector, but to this vector associated to the process x. Okay? Here is also okay, but our enemy is this term. So now, I'm sorry. I'm sorry. G is just a function defined on s times s times s. Just any function. The r times are before, yes, are any times before t1. It's good. You know that, so this is the martingale difference between these two. Okay. I know that if you take this difference between these two the martingale at these two times, the conditional expectation of this difference with respect to the sigma field is equal to 0. So if you multiplied this difference times anything measurable with respect to this sigma field will be 0. This is what I'm using. Okay?
Trying to characterize the law of x.
The law of x. No. If I can erase here n everywhere, finally, because g is arbitrary, because t1, t2, and all the times are arbitrary, finally that permits me to say that this expression f of x t minus integral of 0 t something here will be a martingale. It's okay, or? Okay, I will try to do it with more details later, but until now, that is true. Yep, that is true. Okay. Okay, so maybe I'm not so clear, but I'm just using the usual way to prove that something is a martingale. Okay, no, it's not nothing sophisticated. But so first, my problem is here inside this integral. I need to change that by a function which depends only on the subset in which the Markov process is. So I need to change this Qn. Let me call it which to change this Qn. Yep. By something. Okay, first, sorry. I will write it. First, let me write this expression Qn as, let me fix the J, and so right here, write that like this term, Qn of, Ej. Okay, so that now I would like to change this. So this is the term that I have there, and I will change it by something. Which only depends on the process X. And I have to change this term for this other term inside this time integral. Yep. So these numbers, all these numbers are bounded. Okay, so what I would like to prove is that actually just the okay, no problem, that this expectation is going to 0 as n is going to infinity. This is just that I wish. Okay, this is not true. Not until now, not so far. And of course, no, it's okay. It's okay. So this is what I would like to prove. If I can prove that, I put an n here. Yes, okay. If I can put that, I can erase this term. And I can put here the other term, which only depends on x, here inside the integral. And now this expression will not be equal to 0, but will converge to 0. You agree with me? Yeah, I'm forgetting these numbers because these are just numbers. Bounded numbers, the sum is finite. So this is what I need to, what I will first prove, okay? I didn't prove anything until now. Yeah. Now, again, this is a Markov process. So I can shift the time. Okay, I can shift the time. I need to, here I need to take the maximum over the whole state space. And what I actually will prove is that the absolute value of this is going to to 0. Yes. Now with this, if I can prove that, you can believe that I will be able to change this expression for this other term inside his expectation. Good. Good. This Q Ni is a function defined on my set space, taking values at R. Here you have partition. Here you have your projection. Okay? So I would like to change this function with this other function, which is defined here on S. So what in my mind, I would like to write here, to find here another function Q hat, so that as n goes to infinity, the time average, and we consider this time average, this function is going to be equal to this, the composition of this function. Let me write this expression in another way. So this is the maximum over the starting point of the Markov processes of this expectation, the expectation of the integral from 0 to some t. So this t is just a difference between t2 and t1. Here you have the function q in I of the Markov processes minus this other function qi hat, which is defined on the set S. So apply this. So here you have this. Let me write this composition with a projection function. And now we apply all of this function to the Markov process. Yes. And this is what I would like to estimate. So this expression is exactly this, equal to this expression. Okay? I just rewritten that. Good. Good. So far, what I did is something more or less general. From this point is that I will use something special. I will assume that I have these meta points inside my walls. So from this point on, is that maybe for other models, for other problems, you can use another thing. You can use another idea, another good idea, another better idea. Actually, we are not so smart. So this is our idea. So maybe for sure you can improve it. In our idea, actually in our models, we found some meta points inside the walls. So fix some or choose inside each subset in the partition of the N some points. So at each subset, I'm choosing some points that I call meta points. Okay? under this situation, I will propose to change this function. So my candidate for the function that I put here will be just the. Recall that mu n is the invariant measure in the stationary distribution for the Markov process eta. Okay? I will change this function by the conditional expectation by its conditional expectation with respect to the sigma field generated by the projection function. So QJ, yeah, I changed my, so this is J, sorry, this is J, this is J, everything here is J, J. J is the subset in which to which you are jumping. This is J, and I will define this function J. You need to define a function on the set S, so you need to say what is the value for some I, and I propose to define this Q as the conditional expectation of Qn of the function with respect to the projection function phi. So this I is this I, and here you take the conditional expectation with respect to the invariant measure, stationary measure for the process, Markov process eta, which is nothing else that sum of the subset I, these products, okay? Here you need to divide this by the measure of this subset. Okay, so good. This is, until here, all that I did is something general. And here I propose these candidates, okay? This kind of approach and these candidates for the functions that you use to prove this, what we call, what in our paper we call the replacement lemma. So in another model, maybe you have another idea for another function Q hat. Yes, here I'm using just the invariant measure to take the expectation with respect to this invariant measure, but maybe you have another idea, and it depends on the model, and maybe you have another context in which you know, in your model you don't have these meta points, maybe you have some another idea for that, and then you will try to use another approach. Sorry. Oh, it's okay. Okay, so now, for this candidate, let me see if I can actually prove this convergence. You can write this function as Qj minus Q. So this function times the indicator of some subset I, and you sum over I. Okay? This is clear. Now, this is a finite sum, so I may just focus on one subset I, And what I will actually prove, this is what I wish this is not true. So to prove that, it's enough to examine this expression. I. Okay, we need to estimate this expression. Yeah, that's enough because the number of subsets is finite and fixed. It doesn't depend on n. Good. So once I have written this expression in this form, I can. This allows me to focus my attention on just one subset. Any question? It's okay until now? Yeah.
How did your meta-points actually go into the definition?
Nothing. No, this definition doesn't depend on the meta points.
So you haven't said anything about how you're going to use your meta-points yet?
No. I just made two things. Just define these functions, and independently, I have fixed some points, and now I will try to use it, but I didn't say anything about that. So my way is to prove something with so I will try to prove, and somewhere will appear the actual hypothesis to get my result. So this is just what I wish. Now I will find sufficient conditions to assure that my wish is true. Mm-hmm. So this point, starting point x, is a point in the whole state space. So maybe x is outside this subset I. Okay? Inside the subset I, you have these meta points z. Mm-hmm. Good. And yeah. Here you have the 0, here you have t, and this is an integral over this time interval from 0 to t. Let me look at the first moment in which your process reach, let me put it here. The first moment, so this is my, I didn't use, okay. Let me put a sigma. This is my first moment after 0 when your process reaches the meta point. Let me forget that I here, but no problem. Okay, now consider the first moment after t at which you reach again your meta point. Okay? So, you need to estimate this integral. I mean this integral from 0 to t. But what I can tell you is that this function, this is the function that I am applying here. Yep. To the Markov process. Okay, so if you compute the expectation of this function with respect to the invariant measure mu, the expectation is 0. Okay? So here you have an integral. Okay, you have an integral of some function which has mean zero function of your Markov process. So this is the kind of expression you have here. Okay? The special thing about this function is that the mean with respect to the invariant measure of this Markov process is 0. So the idea here is that if you integrate instead of this time interval, you use this time interval. So that here you integrate from this sigma, from this to this other sigma. Because this function has mean 0, and because at this point, this time, you are in the same point where you will be at this other time. So here you see something like a cycle. Yes, you return, you come back to the same point. Thus, this integral will be equal to 0. Okay, this is something also well known. You can also use here your martingale problem, because when you have a function which has mean 0, and here we are assuming that our Markov process is irreducible, so that the generator of the process is irreducible, then for any function h with mean 0, with respect to the invariant nature of the generator, you can always find some other function g, so that this h is equal to minus L of g. Okay? Now you write the martingale problem for this function g, okay? And you will see here the difference, you will see the difference between the martingales at these two random times, stopping times, but at these two stopping times, the martingale is the same. Sorry. The martingale has mean 0 because it's a martingale, so the martingale is constant, so this difference will be 0. And the other term, which is the function g, evaluated in the position of the Markov process, will be the same, because the Markov process at this time is at the meta point, and at this time he's also at the same meta point. So this other difference will be 0. Okay, so it's a very nice exercise to prove that actually this expectation of this time interval will be 0 if the starting point and the end point of your time interval at that moment, your Markov processes are in the same position. Now, this is 0, but what I would like to estimate is the time interval here over this interval. Yep. So what it remains to do is to estimate the time intervals just over these times, because this is the difference between this interval and this other interval. Good. So you can believe that finally this expression, let me call this expression 1, that 1 will be bounded by twice. You need to do the same thing here and here. You just need to control the time integral from 0 to the first time that you reach your meta point. Which is this is the first time you reach your meta point. And yeah. And here you can take the absolute value. Yep, sorry. Let me write this expression. Minus Q and phi times the indicator of I okay. It's forbidden to raise this line. I missed something. No, it's okay. ds. Okay. It's okay. And of course, in this on this time interval, there is a time that maybe you are outside this space. So during this time, this function is equal to 0 because you have this indicator. So you may assume that actually this interval is starting inside this subset by using the Markov property of the process eta. So here, you can, what I claim is that you can assume that your x, your starting point, belongs to the subset I. Okay? Is someone following me? It's okay for everybody? Okay, good. So you remember that I also needed to prove that for the tightness, yep? This is what I will prove in my replacement lemma. So in my replacement lemma, that will allow me to change the function Qn by this other function, only defined on the finite set S. For tightness, I need to prove that. And so that will allow me to change this Q for this. There is a Qn here. For this other function, Qn. Okay, we have to sum here. But okay, we will be able to change this Qn by these other functions, by these other functions, but you see that these expressions are absolutely bounded because they are just defined on this state space, which is finite. So once you change here that for something that only depends on x, yeah. Once you change that for this, you will have something which is bounded. This time is going to 0, and so this expectation will go to 0. So we really need to prove this replacement lemma. So this is the key result. This is the key result for all my arguments. So if I prove that, I will also get the tightness, which was the first step of my proof. Okay? So you can't forget that. And now I continue. Okay, finally. The replacement lemma will follow if we can prove the following two limits. Let me split these two limits. So on one hand, you will have a maximum over these starting points of the expectation. Here you have, and there is, okay. So this is the hitting time of the meta point. Yeah. This Qn is actually positive, so I can let it like that. Here you need to put the eta n s. Yeah. And here is the indicator. This indicator. So if you can prove that this is going to 0, and so this is the term. This is the expression corresponding to this part. And now for the other part, on each subset, this is a constant. So I can take this constant J. Here I also forget my J. And here you also have a J. So this is a J. And here is the maximum. Over the subset of the expectation of what? The projection of this guy. Yeah? So this is equal to xn s. Sorry. This projection is just already evaluated for this function. So this part here. But now you have the indicator of the process, the indicator of the subset I, and here you have an integral from 0 to the first time that you meet the point, the meta point. Yep. So this can be bounded above by just the hitting time, the expectation of the hitting time. Let me put an I here, because it's the meta point, the subset I. And my other condition would be that this is also going to 0. If you have these two limits, you get that this bound this upper bound is going to 0, and so you finally get the replacement lemma, and then here and then here you can change this guy Can I just erase here? That replacement lemma allows me to replace this expression, this term, by this other term, yeah? Q n, yeah? Here something that only depends on the position, the subset in which you are, and here is no, this is J. Sorry, this is J, and here you have just the function Q, the S, and now it's not equal to 0, but this is going to 0. It's converging to 0. Okay. Okay, now as n goes to infinity. Now, because xn is converging to some, it's okay? Any question? now because this xn is converging to some x, I can say that this term, all this term here, here I can replace this xn by here I can erase the n, just erase the n. You believe me? Here I can just erase the n because xn is converging to x. And now you have that this is true for an arbitrary function g, for arbitrary moment instance before the time t1, and then that implies that the expectation of this expression given the sigma field generated by the function x until the time t1 is equal to 0. Okay? And this expression here is just the difference between is just the difference between these two variables where this variable is just the function x at the point t minus the integral from 0 to t of that, which you could write like a generator applied to the function f yeah, exactly that. So this expression you can write it like this difference where this m is just that. Okay? So I just proved that this process is a martingale process with respect to this filtration. Yep. Okay, so where yeah, exactly. This L is I is Fj minus Fi. This is the sum over J of what? Here you have the Q and yes, so you have an N here. Sorry. You have an N. You have an N. You still have an N. Sorry. Yes, I just skip one step. So here you have your, what was my notation? See, yes. Ej I. Yes, so here I forget one thing. Now, if you are able to prove that that this sequence of numbers, I already tell you that, yeah? If for any I and any j, you are able to prove that Sn is going to fit, they are just numbers. They are just numbers. So if you are able to prove that this sequence of numbers is converging to some number, which doesn't depend on n, it converges to something, let me call this Qij. Then now, in your expression, you can actually erase the n. And now you will finally prove that this is a martingale with respect to the filtration generated by the process X. So you don't have an N here. And then this limit x must be the unique solution of the martingale problem, and so therefore this x will be is Markov. The law of this x must be the Markov with transition rates these numbers. I wrote these numbers like that. With these transition rates. And finally, prove the following theorem. So choose your points inside your well. Define these numbers in this way. So if you can prove that irrespective of the starting point, first these numbers Qn, so these numbers defined in this way. This is just a very simple computation. If you prove that these numbers converging to is converging to some number. Now, if you prove that the expectation of the time you need to get the meta point when you start inside the subset. So this is the time that you need to meet your meta point when you are starting inside the subset. We go to 0. Here, I will multiply. That will be enough because if you have already requiring that this is going to is converging to something, so these numbers must be bounded. Yeah, but just in case you need, let me put here this sequence. Yep. And third, yep. If you have that this time is small enough to defeat this annoying function Qn, yep. Then you may conclude that in law, your sequence Xn is converging to a Markov process by the uniqueness of the martingale problem with these transition rates. These transition rates. Yes, I'm sorry, just 5 minutes. 2 minutes. Sorry. Just to finish with one example, recall my example of the cycles. So this is my subset A1, this is my subset E2. And here, for example, let's choose our meta points, this V and this W. Okay? So, first, if you make the computation of these guys, which is very simple, you will see that these guys are all equal to 1, actually. All they are equal to 1. So this is trivial for that example. Here, the time you need to get these meta points, you remember that here the transition rates were 1, 1, 1, and here n to the gamma, but we need to speed up the process in n to the gamma plus 1. And so when you multiply, you will gain here n to the gamma plus 1, n to the gamma plus 1, and here an n. Yeah? So the time that you need to reach the inside the well, this meta point will be n squared if you are moving at rate 1. But you are half speed up, you process in n to the gamma plus 1, and gamma is bigger than 1, so it's going to 0. So this is also trivial. And finally, this is more than trivial because here you have your indicator, yeah? The indicator. So that this expression inside the integral is equal to 0 if you are if you are not outside if you are not inside the well. So now, what is this function Qn? These functions are equal to 0 here, to 0, to 0, to 0, 0 is equal to 0. And just here, the only rate that you have to jump to the other cycle is this number n. Okay? So, but you need to integrate this function until the time that you reach your meta point. So this is actually equal to 0. And so this other convergence is trivial. So just to making numbers this theorem. Thank you very much. Sorry for getting it.